We're going to begin our next topic related to differential calculus, and to begin discussing differential calculus, we're going to talk about the idea of rate of change. So whenever we talk about the rate of something, we're talking about how does one quantity change in relation to another. So for example, maybe if I was talking about the speed of something, I'm talking about how does the object's distance change relative to time. We could also talk about the performance that people might have in some type of sporting code by using a rate. So for example, if we're talking about Sir Donald Bradman's batting average, we could talk about how many runs has he made per innings, or Michael Jordan's average basketball score, how many points has he made per game. So you can see that we're comparing one quantity compared to another. If I'm looking at this example here, so we're talking about we're filling up a pool with water. Basically, they're comparing how does the amount of water increase per minute. So you can see as time increases by 1 minute intervals, the amount of water we have is increasing by 15 litres. So because the increase in water is the same each time, we can see that we actually have a constant rate of change or a constant rate of increase. If we were to graph this on a Cartesian plane with the amount of water on the y-axis and time on the x-axis, you can see because we have a constant rate of change, that the slope or the gradient of the graph is constant. And I could actually work out what the rate of change is by choosing any 2 points on the graph and determining the slope. So here you can see that we can find the rate of flow of the water by taking 2 points. So we could take the point 1, 15 and 0, 0, and by finding the change, so the change in y, which is 15 minus 0 over the change in x, 1 minus 0 is 15 over 1, so we got 15 litres per minute. What you'll notice, if it's a constant rate, then we will have a constant slope. So when you're working through these questions here, just keep that in mind. The constant slope will mean that there's a constant rate of change. These questions here, when you're asked to find the rate of change of the functions, essentially you're asked to find the slope of the functions. So as you're doing that, just make sure that you're showing all your working out. And then this function here is written. Now, you may or may not be familiar with this terminology where we got f of x is, or this notation, f of x is equal to 5 over 2x minus 3. So instead of writing y, we sometimes write f of x because we're just saying how does the function change with respect to x. So you'll remember this is in gradient intercept form. So we can look at what's in front of the x term, and that's going to tell us something about the gradient, and therefore it's going to tell us something about the rate of change. In all those examples above, we saw a constant rate of change. However, in most real life situations or real world situations, we don't see rates of change that are constant. They often vary over time. So when we have a constant rate of change, we know that the function which represents that rate of change has a constant gradient. However, when we're looking at a varying rate of change, basically we start to see some curves in the function. So here we have an example of a glass of water which has been left out in the sun, and we can see that basically this function is describing how its temperature increases over time. So basically in the first 2 minutes, you can see that the rate in which that the temperature is increasing is quite quickly. And then as time progresses, we can see that the rate of change starts to taper off, which makes sense. When you first have a glass of water out of the fridge, it's going to warm up quite quickly, and then it kind of reaches the threshold to which it's going to be able to warm up, and then it's going to slow down. Now we can find the average rate at which that temperature changes by finding the gradient of the chord which joins any two time intervals. So for example, if I wanted to find the average rate of change in the first 2 minutes, I would find the slope of the tangent between 0 and 2. So I'll draw a straight line which joins those 2 points, and you can see here they found the rate of change by going the rise over the run. So they get the average rate of change is 7.5 degrees per minute. Now, we could change the time interval. So if I decreased the time interval to say 1 minute, I could then find the tangent of that chord, and I'm not going to find the average rate of change is going to be the same. It's actually going to be differing. Okay, and similarly to if I did it maybe over 10 seconds, that average rate of change is going to be different as well, because the rate of change is not constant. So when we find an average, we're going to find that depending on the time interval, that average rate of change is going to differ. So this kind of summarizes that the average rate of change in some function can be found by determining the slope. So this is just talking about how the function's y values change over how its x values change. So if this was point B and this is point A, we can see that f of B, which is this point here, minus f of A, which is this point here, over B minus A is going to tell us the rate or the average rate of change. As you work through these questions in 14a.2, you can see that the functions do not have a constant rate of change, as we see that they're not, the gradient is not constant. Therefore, for example, this one here, this is talking about how distance changes with time. Since that gradient isn't constant, we know that we don't have a constant speed, because there's the way that distance changes with time is changing. We can always find the average by finding the gradient of the chord which joins the 2 points in whatever given time period that we're discussing. So you can apply the same theory to question 2 and question 3, where we're finding the average rate of change in the functions, and also in question 4. Now, one thing to note here, you can see that we started off by finding the average rate of change over 2 minutes. Then I discussed the possibility of maybe doing it after finding the average rate of change after 1 minute. If we were to continue to decrease the time interval in which we're looking at that rate of change over, then we would be getting closer and closer to an instantaneous rate of change, which is the next part of the chapter. But I'll leave that for now, and we'll discuss that in our next lesson. So just work through those questions in 14a.1 and 14a.2, and I'll see you tomorrow. All right, good luck.